we're going to consider an alternative way in this short video of solving ordinary differential equations with schemes that are higher order than Euler's method. And indeed, we can make them arbitrarily high order. And this is a method known as the TaylorSeries method. So the numerical problem for solving an ordinary differential equation is we need to find y of t plus h given y of t, and the only thing that any information we've got is that dy dt is equal to some function of t and y, and we know what that right hand side function is. We also have to have an initial condition, of course. So let's have a look at the Taylor series expansion of y of t plus h. So y of t plus h is equal to y of t plus h times dy dt plus h squared on 2 factorial d squared y dt squared, etc., plus higher order terms. You should know the Taylor series expansion off by heart. This is something that you will likely need multiple times in this unit. And we can simplify that by just replacing this rather clumsy notation with, for example, d cubed y dt cubed is y triple dash. So these two things are identical. This is just a slightly shorthand and neater way of writing it. If we ignore all of the terms h squared and above, so we ignore these terms here, we end up with y of t plus h is equal to y of t plus h times f of ty. And we've already seen that this is Euler's method. This is something that sort of crops up quite a few times in ODE solution. But let's not throw away those terms that are order h squared and above. Let's just keep a couple of them in for the time being. So that's our Taylor series expansion for y of t plus h. If we can estimate what these higher order terms or these higher order derivatives are equal to, then we can find an improved solution to our ordinary differential equation. So what information have we got? Well, the only thing we've really got is that y dashed is equal to f of t and y. That's our ODE. That's that thing there. Those two things are equivalent. Let's take the derivative of this equation here. So the derivative of y dashed is y double dashed. And the derivative of f of t with respect to t, we need to use the chain rule. So that's equal to partial derivative of f with respect to t plus the partial derivative of f with respect to y times dy dt. And of course, from our original ODE, we know what dy dt is equal to. It's equal to f. Okay, we'll come to that in a minute. So again, shorthand notation, it's equal to this. So how are we going to use this in our ODE solution? And probably the best way of doing this is to actually consider a concrete example. So the example I'm going to give is solve dy dt is equal to negative twice t minus y. And we have an initial condition of y naught is equal to minus 1. And we're told we want to have a scheme that has an error that's order h to the fourth. So let's consider including these first two extra terms here, because the next term down here is a plus order h to the fourth term. If we calculate the second derivative from the ODE, so this is the ODE encircled in green here, the first derivative is equal to minus twice t minus y, therefore the second derivative is just equal to minus 2 minus y dashed, we're just taking the derivative of this here, or we know from the original ODE that y dashed is simply equal to minus twice t minus y. So we substitute that in for y dashed, and we end up with y double dashed is equal to minus 2 plus twice t plus y. So we've used our original equation here again. We can also calculate the third derivative from the second derivative term, and we do pretty much the same thing. And it's pretty easy to show that y triple dashed is equal to 2 minus twice t minus y. So if we substitute y dashed is equal to this, y double dashed is equal to that, y triple dashed is that, into our Taylor series, so we're going to substitute this for y dashed, that for y double dashed, and that for y triple dashed. Again, it's easy to show that y of t plus h is equal to y of t plus h times the first derivative plus h squared on 2 times the second derivative plus h cubed on 3 factorial times the third derivative plus an error term that's order h to the fourth. So if we group the terms in y, in t, and the constant terms, we can show that y of t plus h is equal to 1 minus h plus h squared on 2 minus h cubed on 3 factorial times y of t plus negative 2h plus h squared minus h cubed on 3t minus h squared plus h cubed on 3 plus an error term. So what we have done now is we've got a much higher order solution for this particular equation. So while this method can sometimes be used successful, I'm sure you can see that there's potentially some problems. It must be applied in a case-by-case manner. So every problem is going to be different and we'll have a different y update. So if we change that right-hand side function, we've got to go back and completely redo what the problem looks like. So mathematical analysis is required before the details are determined. So before you can begin programming this, you need to know exactly what equation we're solving. And ideally, you don't want to do that. Ideally, you would like to develop a method that can handle any right-hand side at all. And so consequently, the method cannot be coded generically. And every time you change the ODE, you need to create a bespoke solution. Another thing that you need to worry about is with this method, stability is not guaranteed. And of course, you have to assess this for each new application. So although the TaylorSeries method is an interesting idea, in practice one needs to be careful using it.